Okay, so this is a chapter about the chapter 26 about resistor. Okay, so first we'll introduce electric current and the current density, and then we'll also introduce the resistance and resistivity. Then we'll introduce Ohm's law. Probably you have already learned it in high school physics. And then we will slightly talk about the power semiconductors and superconductors. Okay, so for the electric current, okay, so it says any isolated conducting loop, regardless of whether it has excess charge， 就是它是不是有带静电荷，没有关系 ，OK。So an isolated conducting loop is all at the same potential， 就是如果这个 loop 它只要没有静电荷。或者是就算有静电荷也行了，它如果是有一个电流在循环流动的话，那我们还是看作an isolated conducting loop，应该是说它没有电流的话，它如果没有电流，它就算有电荷，它有电荷也好，没有电荷也好，整个导线都是同一个 potential 啊，整个导线都是同一个 potential。So no electric field can exist within it or along its surface。它的里面跟外面都不会有啊 ，within it 或者是在表面啊，都不会有电场。Okay, but here we try to do something different. We try to insert a battery in the loop. The conducting loop is no longer at a single potential. No longer at a single potential. Electric field act inside the material, make up the loop, exerting forces on internal charges, causing them to move and thus establishing a current. OK, 所以现在的话，我们是加一个电池啊，左边正右边负，那它就会有电流啊，电流的方向是从正极处来，然后沿着路跑到负极，从正跑到负。那电子流动的方向的话是反方向的，因为在19世纪初刚发现这些电学的效应的时候，他们还不知道有电子的存在，所以当时他们是定义了电流是从正到负的，他们的想象中是他们是一些正电荷这样流动，他们也是按照这个方向去定义这个电流。所以就按照这个假设去建立了整个电学了。所以它后面就算发现了电子是负电荷的话，没有正电荷在流动，他们也没有再去改这个电学，因为它已经建立得很好，它没有这个勇气去没有梁静茹给他勇气去改这个符号了啊。OK， 所以OK， 所以就是这样。所以当我们有这个电池的时候，它里面就会有电场了啊。之前讲到导体里面没有电场是我们没有给它 potential difference 的时候啊。现在如果我们给了一个电池的话，它就会有 potential difference 因为这个电池本身就是一个 potential difference， 那有 potential difference 的话，那在这个导体里面也会有电场去推动这些带电粒子或者是电子也好，正电荷也好去流动。Okay, so yeah, so here is try to mention a section of a conductor part of a conducting loop in which current has been established is if charge dq passes through a hypothetical plane， hypothetical plane 就是一个假想的平面 假想的平面。In time dt, okay. If charge dq pass through a hypothetical plane in time dt, then the current I through that plane is defined as this one, okay. I 等于 dq dt I 等于 dq dt。OK， 所以它的意思是比如说有个导体，我们有一些假想的面，就比如说 AA prime 是一个假想的面 ，BB prime 也是一个假想的面 ，CC prime 也是，就好像你去看赛车，它就有一个终点线，那个终点线的话就是一个假想的一个线，它不是一个实际里拉一根线。所以如果车通过的话，就是通过那个终点线是一条假想的线。那现在的话，就是一个单位的时间，或者是一个很短的时间之内，因为其实你的电流不一定是一个常数，所以它用一个微积分去定义，就是在一个很短时间里面，有一个电流通过它，那它的电流就是这个 dq 除以 dt， 也或者是说对于 q 去求那个时间的导数。Okay, so the current is actually the derivative of the charge with respect to time. Okay, for a given hypothetical plane, such as AA prime, BB prime, or CC prime. Okay, so here we will introduce a law called the Kirchhoff current law. Okay, so here it says a conductor with current I0, current I0 splitting at a junction， 就是有一个junction 中文不知道是什么，就是路口还是交接点吧。Splitting at a junction into 界面into two branches 就是开叉的意思嘛，就是一条路I0 coming from the left hand side and then it's split into two paths, two branches. Okay, so this one we call the junction, and then because the charge is conserved, the magnitudes of the current in branches must add to yield the magnitude of the current in the original conductor, so that I0 equals I1 plus I2. OK， 它的意思是电荷守恒嘛，那电荷守恒，所以DQ0、DQ1、DQ2。这三个也是守恒嘛，就是它总的量不会变，就是DQ0 从这里过到这里来然后分两路，那两路的话它总和会不会变，就是 Q0、Q1、Q2 不会变，所以它的 delta 它的 D 也不会变，它的 DQ0、DQ1、DQ2 也不会变，所以它们的导数对时间的导数也不会变。也就是说 I0 等于 I1 加 I2， 所以是电荷守恒。那我们把这个叫做 Kirchhoff current law， 这中文叫做柯西和夫定律了So in short form we will call it KCL. KCL. This is not the chemical formula, not the potassium chloride. 那不是氯化钾了不是那个化学式不是 potassium chloride， 这个叫做 Kirchhoff current law Another one, we still have one a law called the Kirchhoff voltage law. We will learn it later. Okay, and for this one, it is the short form is KVL. So we have KCL, KVL to solve most of the circuit. For solving RLC circuit, KCL, KVL is sufficient. Of course, we still need something like the Ohm's law and also the V equals L d I dt or I equals C d V dt for the for the capacitor and inductor. Yeah, but we mainly use the KCL or KVLs to solve for the RLC circuit, or even some other circuit. We can still make use of it because the assumption for these two are quite fundamental. It is for KCL is about the conservation of charge, and the KVL is, you can regard it as the definition for the electric potential. It is something like starting from a point to another point. Okay, you take this path or take that path. Okay, so actually we assume that there is a potential difference V. Okay, so this is I, this is F. So if you take integration of E dot ds and then negative for the path 1, okay, will be negative integration of E dot ds, okay, for the path 2. Okay, so this is what we have learned in chapter 24, and this is related to the KVL, but we'll talk about that later. Okay, so here we also introduce a variable called the current density. Yeah, but this definition is a little bit strange. Usually when we try to define a variable, usually it will be something like this variable equal to something else, but here it's not that case. So for this one, the definition here is here. The definition of the current density J, we put it in the surface integral. Rather than making it like J equals to something else. Because if we really need to write it like that, it will turns out to be something like a gradient. It will be something like J equals to a gradient of I, something like that. Something like that, or gradient Q. I don't quite remember. Maybe gradient of rho, something like that. Okay, but we'll talk about that later in chapter 32. We'll talk about that in chapter 32. So here we just accept that this is the definition of J because it makes things a little bit more easier. At least it is only a surface integral 就是它只是一个面积分用这个面积分来跟这个把这个 current density 这个电荷密度跟电流拉上关系，所以就是这个电荷密度乘以这个面积嘛，乘以面积的积分那就是电流，就很直觉就是这样的密度乘以那个维度回去它就变成那个量。Okay, so here the SI unit for J will be A per meter square. Okay, A is the SI unit for the current. Okay, so for the I, the SI unit is A. Okay, so here is A per meter square. Okay, and then dA is meter square. So this meter square cancel out, so it becomes A for the I. Okay, so here it says the current density J has the same direction as the velocity of the moving charges. If they are positive charges, the opposite direction if the moving charges are negative. 就是刚才说的，就是如果动的是正电荷的话，那电流或者是电流密度的方向就是正电荷的流动的方向。如果是负电荷的话，它就是相反的 ，I 跟 J 跟这个负电荷流动的方向是相反的。 Okay, so here we try to derive a, equation here relating to the drift velocity and the current density. Okay, so it will be useful for physics, but actually I'm not a physics guy, so I seldomly use that. But when I learn the physics tool, so yeah, of course it not in UM, but when I learned that there's a physics professors, then yeah, mentioned that the equation is very important, yeah, for them for their research. But yeah, I have never used this equation later on. Okay, but anyway, we slightly talk about that. So here the assumption is that we have a wire, So conduction electrons are actually moving to the right, but conventional current I is set to move to the left. Okay, so here we assume that the current is moving from right to left. And here we also assume that the conducting electrons, Okay, so we assume that it is a positive charge, E moving to the left side. And in that case, as much as we have a current, we have positive charge will moving to the left side. So there should also be E field pointing to the left side, so that the positive charge will be pushed by this E field to the left side. And in that case, as much as positive charge moving to the left side, which means the current density is also pointing to the left side. Okay, so here we have Q equals E times this NAL. What is NAL? So N is the current density. I mean the charge density. The charge density is N. N is the charge density. A is the cross-section area, cross-section area, and then the length is the length. L is the length. L is the length of this wire, at least for this part. Okay, so actually, what it means is that this is the A times L is the volume. A times L is the volume here, and then N times this volume will be the number of charges in this part, and then this is the charge amount of a single charge. So this is the number of charge times the charge amount of a single charge. So this is the total charge within this part, And here we assume that it takes time t for a single charge to start from here to go to the endpoint. Okay, start from here to there. So which means T is actually L over Vd. Vd is the drift velocity. Vd is the drift velocity. DRIFT, drift velocity. Drift velocity of a charge. OK， 所以就很简单嘛，就是长度除以那个速度，就是那个时间啊。OK, so here, as much as we assume all the things are constant, so I equals Q over T rather than dQ over dt. Okay, because if it is a constant, then we can just take a larger range. Okay, larger range here, Q divided by the total time T. So I equals Q over T. Okay, so Q is this NALE, putting it here. T is L over Vd, putting it here. So L and L can be cancelled. This L and this L can be cancelled. Okay, so finally we have N times E, putting it here, A putting it here, Vd putting it here. So this is I. And previously, yeah, we have a J equals IAY. So Yeah, originally the definition should be like I equals integration of j dot d8, j dot d8. Here we don't have a circle. We don't have a circle here, because it is just a open surface. It is not a closed surface, so we don't have a circle here. Yeah, for the Gauss law, it is for the Gaussian surface, which is a closed surface, so we have a circle there. Here we only have an open surface. So in this case, if we assume that j and dA point to the same direction, and so j dot dA becomes j times dA, and j is a constant. We also assume that, so it finally becomes a j times a. So we have j equals I over a. So which means that we try to move this to here, so it becomes I over a. So finally we have a j equals NE times VD, NE times VD. So this is the formula we would like to derive. So it actually tells you that the current density is this expression. So within the bracket, n is the charge density. Is the charge density. It will be a constant for a specific material. 就是当你选定好一个物质之后，它的电荷密度是固定的，或者是你温度也不会变化的情况之下，它的电荷的密度是固定的只跟那个物质有关比如说这个是铜，这个是银，或者是其他的金属只跟那个金属的那个本身有关所以当你固定了那个电线那根线的材质固定了之后，它就是一个常数。那 E 当然E is of course a constant. It is the elementary charge. So and finally, which means that J is proportional this drift velocity, the drift velocity. So if the drift velocity is faster, the current density is larger. Okay, so this is what I just mentioned. The drift velocity is related to the current density by this equation. So here the product Ne, whose SI value is the Coulomb per cubic meter. Okay, C per meter square. Is the carrier charge density. Carrier charge density. 就是这个是电荷的密度电荷的密度。那这个 carrier 的意思是载体，就是这个电荷这个电荷的，有可能它只是一个单纯的电荷，有可能它是一个比较大的一个粒子，或者是大的分子之类的，或者是大的离子它就不一定只是一个单纯的电荷，所以它叫做一个 carrier。但实际上我们知道一个固体里面它就只有自由电子，是一些负电荷的粒子。Okay, so here we have a sample problem. So it says the current density in a cylindrical wire 就是一个圆柱形的导线 of radius r 2 mm is uniform across a cross section of the wire and is J equals this value is a constant. What is the current through the outer portion of the wire between the radial distance r over 2 and r? Okay, so as much as it is a constant, so A prime will be pi r square minus pi r over 2 quantity square. Okay, because we only consider the outer ring, the outer portion from r over 2 to r. Okay, so which means that the cross section for that part will be the whole circle subtracted by the inner circle. Okay, so it will be like that. So it is actually pi over r squared times 3 over 4. Okay. So this is nothing but 3 pi over 4, 3 pi over 4, and then times r squared. R is 2 times 10 to the negative third power, and then squared. So this is 9.42 times 10 to the negative 6 meter squared. Okay, so as much as we already know the cross section, and then the j is a constant, we already know, so I will be j times a prime. So this j is 2 times 10 to the 5th, and then times 9.42 times 10 to the negative 6. So this is a 1.98. So this is a very easy sample problem at the beginning for part A. Okay, and then for part B, okay, it makes it a little bit more complicated because here the j is not a constant anymore. It is related to the radius. So you can simply imagine that we need to do some integration. Okay, so suppose instead the current density through a cross-section varies with radial distance r as j equals a r squared. A has this value and r is in meter. So what now is the current through the same outer portion of the wire? Okay, so here we actually need to use the surface integral. Okay, so here, this is the surface. So dA is proportional, is perpendicular to this surface. So dA is either pointing out of the page or pointing into the page. It only needs to perpendicular to it. As much as it is not a closed surface. For closed surface, you must define dA is pointing outside, but this is an open surface. So the dA only needs to perpendicular to it. So it can be either pointing into the page or pointing out of the page. But it doesn't really matter for this case. So So because it doesn't tell you what is the direction of j either. So of course we will also assume that j and dA points to the same direction. Let's say j is pointing into the page, the dA is also pointing into the page. So j dot dA becomes j times dA. Okay, so j is ar squared. So integration of ar squared and dA. I'm not sure whether you still remember. So for this one is a cylindrical coordinate. So for this dA, for this part, it is like a polar coordinate. For the polar coordinate. So for the polar coordinate, it is something like this. Okay, this is the dA. Okay, this is dr. And this part will be r times d theta. This is d theta. So this area dA will be dr times r d theta. Okay, so it becomes dA becomes r dr d theta. Okay, and actually this is a double integral. So we need to determine the lower and upper limit. Okay, actually it asks you the r is from capital R over 2 to R. So we only integrate dr from capital R over 2 to R rather than from 0 to R. But for the theta, it includes the whole 360 degree. So it is 0 to 2 pi. Okay. So it becomes A is outside, A is a constant, and then we have R cube dr. We also have d theta. Okay, integrate from 0 to 2 pi. This is integrate from R over 2 to R, like this. Okay, so this is easy. So this is A, and this one will be R to the 4th power over 4. So this is R to the 4th power over 4, and then minus R over 2 whole to the 4th power, and then over 4. Okay, so this is this one, and then for this one, this is nothing but 2 pi. Okay, because it is integrating 1, it will become a theta. Evaluated from 0 to 2 pi, it is 2 pi minus 0, which is 2 pi. Okay, so finally we get this thing. So this is nothing but 15 over 32, and then AR to the 4th power pi. Okay, so we not only need to substitute the number. 15 over 32 times A is this one, 3 times 10 to the 11th power, and then times 0.00. Okay, what is R? R is 2 millimeter. So 0.02 to the 4th power, and then times pi. So this is 7.18. Okay, so for this one, for part B, as much as the J is related to the radial distance R, so we need to use the integration. Okay, so yeah. So more generally, dA will be like this, which is R dr d theta, But yeah, if you jumping some step, sometimes it will be written as dA equals 2 pi r dr, something like this. It just skip through the theta, yeah, because you already assume it is the whole circle for the 0 to 2 pi. So this 2 pi directly come out. Sometimes the textbook will write it out like this. From another point of view, you can consider like we try to cut it out. This small ring, we try to cut it out and then flatten it to be a rectangle. So the height of it is dr, and then the width of this rectangle will be 2 pi r. So this is dA becomes 2 pi r dr. Okay, so this is another point of view, without considering the more general polar coordinate. And actually, it gives you the same thing. If you just put this one to here, okay, you don't need to bother with the d theta, okay. So you only have the integration of dr from r over 2 to r, okay. This one already become 2 pi. Okay, so here, sample problem 26.03. Okay, so it says, so what is the drift speed of the conduction electrons in a copper wire with radius r equals 900 micrometer when it has a uniform current I equals 70 milliA? Assume that each copper atom contributes 1 conduction electron to the current, and that current density is uniform across the Y cross section. OK， 所以我们现在这个要求的是什么？是这个电荷的速度啊。 他一开始就问 What is the drift speed or drift velocity of the conduction electrons in a copper wire 在一个铜的导线里面 Okay, so we'll make use of this one. We'll make use of this one. So yeah, we don't actually need to memorize this one, but yeah, actually we can somehow write it out. Yeah, we can somehow write it out. Let's see what is the meaning here. So N here is the atomic per unit volume. Okay, so it is actually the particle density. Okay, the number of atoms per unit volume. Per unit volume 就是这个单位体积里面有几个这个电荷的粒子数目啊。OK， 所以这个的话，它就类似是乘一些数除一些数，因为你看到 atom 出现在这里 ，volume 出现在这里，所以它中间的话就是乘一个 mass 除一个 mass， 然后就乘一个 mole， 然后除一个 mole。啊，这个很化学了，这 mole 是什么我都忘记。反正就是说，它这些数为什么要它要这么乘一个数除一个数？因为有一些数能够在表里面查到的，就比如说在 Appendix F 里面，它可以查到的是铜的密度，铜的质量密度是8.96克每立方厘米，然后这个铜的 molar mass 每摩尔的质量是这个63.54克每摩尔，那这些数就可以带进来这边当然有些是倒数，就是比如说这个是 density of copper 的话，就是 mass per volume mass per volume， 当然你要转一下这个SI unit G 变成 kg， 然后 cm 立方变成 m 立方，然后这个是 molar mass per copper 是这个倒数了，这个是 mole per unit mass 跟这个是倒数，然后也要转一下这个 G 要转成 kg， 还有这个什么 Avogadro 乘数Avogadro number Na 等于这个6.02乘以10的23次方每摩尔。Okay, so yeah, we have all this number and then plug it here. Okay, and then this is pretty much it. Okay, so this one is actually Na. This is 1 over m is that one, and then rho copper is the first number. Okay, but we need to convert all of them to a proper SI unit. Okay, so we can just substitute the number. Na is already SI unit 6.02 times 10 to the 23rd power, and then times 1 over m. M is this one. Yeah, but actually it is 63.54 times 10 to negative third power. 10 to negative third power, because this is G. Okay, make it a kg. We need to divide it by 1000. And then here is 8.96 times 10 to the third power. Okay, so making it G to be kg, we need to divide by 10 to the third power. Okay, 10 to the third power. And then here cm cube. Cm to m is 10 to the second power. Okay, cube become 10 to the 6th. Okay, but here is a new denominator, so we need to multiply by 10 to the 6th power. Okay, so 10 to the 6th cancel with 10 to the 3rd. Okay, becomes 10 to the 3rd here. Okay, so here we have 8.49 times 10 to 28. Okay, per meter cube. 因为这个一开始是说这个是粒子的密度，就是在每一立方米里面有多少个电子有多少个电子，就是这么多个。Okay, so here we can make use of VD equals J over NE. And actually J is I over A. So we have I over NEA. Then we can plug in all the numbers. Okay, so A is 17 BDA. So 17 times 10 to negative third power. And then N is this one, 8.49 times 10 to 28 power. Okay, and then E is 1.6 times 10 to minus 19. And then A, where is A? A is related to this radius, okay, pi r square. So pi r square is actually pi and then 900 micro, 900 times 10 to negative 6 and then square, like this. Okay, so the velocity is 4.9 times 10 to negative 7 meter per second. 这个速度啊很慢哦，很慢。它每秒只移动4.9乘以10的负7次方米啊。那这个的话，你换成 SI unit 的话，就是你要不然就写0.49个 micrometer per second 啊，要不然你也可以写490 nanometer per second， 都是很短的，反正都是一样的数字。就是说，在铜线里面，这个位移，就是这个漂移速度啊 ，drift velocity of an electron is only 4.9 times 10 to negative 7 meter per second， 就很慢啊，就是广东话就叫做慢過隻蝸牛啊，慢過隻蝸牛，slower than a snail 啊，那为什么呢？为什么呢？因为其实这个电呢不应该那么慢才对啊。就比如说，电灯在哪里？在 power on， 好像不是，这乱按，灯嘛，白板灯，这个也可以啊，这个也可以，白板灯。没有反应。有反应，有好像后面有一点后面。后面吗？后面上面有个灯。后面上面。白板顶上有个灯。算了，我不按了。反正那个意思是，比如说一个开关在某个地方，我一按，它其实马上1秒钟之内它就会开或者关啊，你明白我意思就好。我不做这个动作了，因为我找不到那个开关了。那意思是，其实它不应该那么慢啊，因为这里算出来的是4.9乘以10的负7次方。如果比如说要从这里传到一个灯，在一个比较远的地方，那个少说也是1米以上嘛。那如果你用1米去除这个速度，岂不是要什么100万秒吗？100万秒很长啊，100万秒很长，要很多小时啊，一小时才3600秒嘛，10的3次方嘛，你还要要很多天的时间才跑到的。那是不是这个数字是有问题呢？其实是不是的，是因为说，它如果那个电子要跑到那个灯去给它消耗的话，其实是一个类似排队的这样。就比如说我现在有一个电灯泡，不会画，这样吧，怎么画出一个笑脸？不会画电灯，这样吧 ，OK。那比如说这里有一个开关我放大一点好了，比如说这里有一个开关，那我打开的时候，其实是整个就比如说在某个地方有个电池吧，在某个这样画好了比如说这里有个电池。那这里正电和这里负所以有一些电子其实是整个导线的电子都在排队都在排队，所以其实怎么说，就是我把它 打开的时候，当然所有的电子都原地不动，它没有办法动那这个灯也不会亮。那我把它闭合之后，那这些电荷就是按照这个 drift velocity 很慢的，它其实也是一个推一个排队这样一个个进去给它给消耗然后出来就没有能量。那大概是这个意思。所以其实那个电子的漂移速度这个是算的没有问题，当然它不一定很准它不一定很准，它只是一个大概的数字，但是它的 order 它的次数的话其实是 OK 的，就是它的准确的值当然跟实际可能有一些差距，因为我们做了不少的假设得到这个公式得到就比如说这个 J 等于 VD 乘以 NE 这个公式有一些假设在里面。但是它其实它的物理上的意义是其实这个电荷要一直往前跑，它还是维持着那个速度只是说排到的那个地方就给它给消耗。OK， 我们还可以讲一点。Okay, so here we talk about the resistance and resistivity 这个叫做电阻跟电阻率这个 resistance 叫做电阻或者电阻值电阻值。这本书很奇怪，就是 resistors 跟 resistor 它不会分我们一般就是电阻会叫做 resistor，电阻值叫做 resistance 然后这个叫做电阻率。类似的话就是上一章讲的这个 capacitance 是电容值电容值 capacitor 才是电容但是这本书就没有出现过电容，也没有出现过capacitor， 没有出现过 resistor 这样的值这个是电阻这个是电阻很奇怪的Okay, so here it says if we apply the same potential difference between the ends of the geometrical similar rod of copper and of glass, very different current results 所以他说就是不同的物质比如说铜线或者是一根玻璃的话给它同样的 potential difference， 它的特性它电流就会差很多。The characteristic of the conductor that enter here is electrical resistance 所以这个特性我们就把它叫做有一个电阻值电阻值 The resistance R of a conductor is defined as R equals VR. So simply speaking, is the Ohm's law 欧姆定律。Okay, so we already know V is volt per meter. The SI unit for V is volt per meter. Is volt. Is volt. So the SI unit here is volt. The SI unit for the current is A. Okay, so the SI unit for the R. Of course, you can write it as a V over A, but usually we will write it as ohm. Ohm. Or using this Greek letter. Okay, this is omega. This is omega. This is the capital letter of omega. The small letter of omega is like this. This is a small letter. This is the capital letter of the omega, which is the last letter of the Greek letter. 就是最后希腊字母的最后一个字母是 omega。OK， 所以这个是 SI unit omega。Okay, so V is the potential difference across the conductor, and then I is the current going through it. Okay, so usually we will use a symbol like this. Okay, to specify this is a resistor. And then pay attention to the direction. Okay, so if we have V, okay, this one has a higher potential, this one has a lower potential. The current I is going from top to bottom. Going from top to bottom. We always define the definition, the direction like this. Okay, so for the V, let's say this one is positive, this one is negative, this one has a higher potential, this one has a low potential. So the I will be like this. Even for a capacitor, if we have a voltage or potential difference like this, the current, we will still define the current direction like this. And so as the inductor. For the inductor, we'll learn it in chapter 30. Okay, so the V like this, and then the I is also like this. We always try to define the direction of the current with respect to the potential difference like this. And in this case, all the VI will have the same polarity 它们都是一起是正的，或者都是一起是负的。Okay. And here we have another formula. We have another one. This one is called rho. This one is called rho. Rho is the resistivity. 我刚才说的这个是电阻率。Okay, so this rho is equal to E over J. Inside the conductor. Okay, inside the conductor. Suppose we put a voltage, we put a potential difference across this conductor. There will be current. And there will be E field. So this E divided by J will be the rho. And actually, this rho is only related to the material. This rho only related to the material. 就只跟材质有关的，只跟材质有关 material only related to the material. But for the resistance, this one is related to material and also the geometric shape. Geometric shape. 它跟它的几何的大小有关几何的大小，电阻值跟几何的大小有关，那也跟它的材质有关，而这个电阻率的话，只跟材质有关，跟它的长宽比没有关系它跟它的几何的形状没有关系。Or if we try to write it like this, E vector equals rho J, we can call it the vector form of the Ohm's law. Vector form of the Ohm's law. 我上物理的时候，那个教授也是很喜欢这个式子，但是其实我们也是没有用过，因为物理人才会用这个式子。然后他说这个是这个欧姆定律的向量形式所以他做物理的研究的话，也许就会比较有用。那我们工程，我们做电路的话，其实我们是尽量避免去跟这些向量有关系，因为向量的话处理起来就很麻烦，所以我们做电路的话，通常都是只用 I 跟 V 去计算就不会去接触这些向量，尽可能去避免。那这个是 E 等于 rho J 的话，我们叫做向量欧姆定律的向量形式。类似的话有一个 reciprocal 导数，这个 resistivity 的导数叫做 conductivity 有这个东西，我觉得不用记太多了，就是反正他们就是他们是导数的关系，这个是导电率，就是电阻率越大的话，导电率就越低，就是一个是 电阻率的话就是电子比较难通过啊，越大的话就越难通过啊。电导率的话跟它相反，知道这个就好，不用记太多这种符号了啊。反正它只是书本里面有介绍一下。OK，那我们。